Welcome to my report on the week 13 reading. This week we only have one video to watch about electromagnetic radiation. In this video we recap Coulomb's law, the Biot-Savart law, and looked at more general equations for electric and magnetic fields, discussed the representation of fields, saw that accelerating charges cause radiation and some visualizations of that, as well as how the velocity of propagation, electric field and magnetic field are related, and how solving the Maxwell equations gives us the relationship between electric radiation, the magnetic radiation, and the speed of light. This lecture covered a lot, but I was familiar with a few of the topics from previous lectures. This was the discussion of Coulomb's law, Biot-Savart law, Gauss's laws, and Faraday's law. In previous physics classes, we've discussed radiation, but in the context of what this lecture covered, it was a new topic for me. The first thing we covered was a recap of Coulomb's law and the Biot-Savart law. These laws govern electric and magnetic fields when they are time independent, or when they change very slowly with respect to time. They are called electrostatic and magnetostatic respectively. We then discussed these fields and the equations which govern them more generally. These are the equations you can see here. They are Gauss's law, Faraday's law, and the Maxwell-Ampere law. They are collectively known as Maxwell's equations. We then moved on to the concept of electromagnetic radiation. The first thing we did here was to consider the representation of fields in a different way. Rather than using arrows, we can instead use lines that show the path the arrow would take. Electromagnetic radiation is caused by accelerating charges. By having the charge accelerate, the new electric field needs to propagate and causes a kink in the electric field. It is this kink in the field which we are interested in. The first thing to know is that the electric field at this point is pointed in the direction of the kink, and the velocity of the propagation is pointed perpendicular and away from the charge. By solving Maxwell's equations, we can find that there is also a magnetic field B, which is perpendicular to the electric field. Additionally, these equations tell us that the direction of the velocity is equal to the cross product of E hat and B hat. We're also told from these equations that the propagation speed is the speed of light. One of the final things we discussed in this lecture was the radiative electric field due to a point charge, which is given by the equation for E sub r, which you can see here. This gives us the E radiative. The vector A perp is the component of the vector of acceleration which points perpendicular to r. Mathematically, we can find A perp using the equation for it, which you can see here. Lastly, we saw the relationship between the magnitudes of E radiative and B radiative, which is that the speed of light is equal to the magnitude of E radiative divided by B radiative. Following this, we covered a couple of examples seeing these concepts in actions, and at the end of the lecture, it was stressed heavily that this type of radiation is only due to a charged particle, which is accelerating. I think the most difficult concept we covered today was the Maxwell-Ampere law, as it's not something we've looked at before, we've only touched on very briefly. However, having read the physics book page about the topic, I do feel a bit more comfortable with the concept. Thinking about this concept, electromagnetic radiation, in the context of my major, which is computer science, I'm particularly interested in how radiation is used to transfer information. We spent a small section of this lecture talking about how it's used for transferring data over cellular networks and Wi-Fi. This is something I'd like to learn more about. Thank you very much for listening.